Have you ever wondered why time exists at all? Not how we measure it with clocks, but why reality looks like a movie instead of a single photograph. What if I told you that at the deepest level, the universe can be described without time, and yet from that timeless description, our flowing time somehow appears? Today we will imagine a universe with no time, and from that impossible picture, we will build an explanation for why time exists for you and me. Let's start by imagining absolute stillness. Everything is not just quiet, but absolutely frozen. Planets have stopped in their orbits. Light has stopped traveling. On Earth, a lightning bolt is captured as a single stripe. Our heartbeat, our thoughts, everything fixed in one unchanging arrangement. That is a timeless universe, a single eternal snapshot with no before and no after. Now notice the paradox. If nothing changes, how could anything occur at all? Change seems necessary for experience, right? After all, we can only think because our brain changes states. We can only remember because patterns change and leave records. So how does this timeless universe work at all? Apparently, it seems like a timeless universe is technically possible as a mathematical description, but it is useless as an arena for events, processes, or minds. Well, no, it is not. Surprisingly, some of the deepest equations of modern physics do not include time in an explicit way. When physicists try to merge quantum mechanics with gravity, time often disappears from the fundamental formulas. Those equations say, in effect, that the universe is a set of possible configurations, and the laws relate those configurations to one another without invoking a universal clock. What we think of as time can then appear as a secondary feature, an emergent ordering of differences between configurations. This idea sounds abstract, but it leads to a powerful insight. Time might not be a primary ingredient of reality. Instead, time could be a way of tracking change, a bookkeeping tool we and the universe use to order the transitions between different states. To make this concrete, think of a deck of unique playing cards. If all the cards were identical, you could shuffle forever and never know you had changed anything. But if each card is different, rearranging them creates a sequence you can detect. Similarly, the universe is full of distinguishable configurations. When one configuration differs from another, you have a notion of before and after. That relational difference is what we call time. Put differently, time is a label for ordered differences. It is not a substance that flows from left to right. It is the pattern you read off changes in the world. How does a timeless underlying description turn into the rich flow of experience for creatures like us? The answer is records. Whenever a physical process occurs, it usually leaves traces, footprints, broken branches, photons scattered, and memory patterns in the brain. Those traces form correlations between parts of the universe. If a configuration contains records that point to another configuration, an observer embedded in the system will read those records as evidence of a past. So a sequence emerges. Configuration A contains records that look like configuration B, and configuration B contains records that look like configuration C, and so on. An embedded observer interprets that ordered web of records as a timeline. This is how flow arises out of static relations. A separate but crucial ingredient is entropy. Entropy measures how many microscopic arrangements correspond to a macroscopic state. Low entropy states are special and ordered. High entropy states are generic and disordered. The reason we experience time as a one-way procession from past to future is that the universe tends to move from lower to higher entropy. Think of a tidy desk and a messy desk. There are far more ways for a desk to be messy than ways for it to be tidy. Given many micro changes, the desk will almost always become messier. That statistical drift gives the arrow of time its direction. If the universe started in a very low entropy condition, then entropy increase provides the thermodynamic bias that makes records reliable and makes a sequence of configurations readable as a past and a future. At the quantum level, the transition from possible to actual involves entanglement and decoherence. Quantum systems do not live in single definite states, but in superpositions, and when systems interact with large environments, the delicate superpositions decohere into effectively classical alternatives. Decoherence is not a magical collapse. It is the process by which quantum probabilities become robust, stable records that an observer can read. When decoherence produces stable records, it supplies the differences that an embedded observer uses to order events. So quantum mechanics contributes both the degrees of freedom that can change and the mechanism that turns those changes into readable facts. Putting this together gives us a picture where time is emergent rather than fundamental. The underlying description may be a landscape of configurations connected by relational laws. Entropy and the statistical directionality of macrostates provide a global bias. Decoherence and record formation produce local, readable sequences. An observer, embedded in that web of records, experiences a directed stream of moments and calls that stream time. In short, time exists because change exists, and change becomes meaningful when there are more probable configurations to move into and when those moves leave retrievable traces. You might object that this makes time feel unreal or subjective, but that is not right. The emergent time described by physics is as real as anything else we trust. It governs cause and effect, it constrains what can happen, and it is indispensable for life, memory, and prediction. Saying time is emergent is not saying it is illusory. It is saying that the property we call time is a robust, reliable feature that arises from deeper processes. Another worry is whether this framework can answer whether time travel is possible. The thermodynamic arrow and the requirement for reliable records make macroscopic time travel essentially impossible. Tiny quantum tricks like microscopic tunneling can shuffle individual degrees of freedom, but reversing the vast increase of entropy that composes a whole moment of experience is statistically absurd. Let's use a metaphor that helps us understand this. Think of the universe as a massive photo album where every page is a possible configuration. If the pages were unnumbered and uncorrelated, you would have no sense of order. But if some pages contain photonegatives or notes that point to other pages, you can start to read a story. If the album has a tendency to progress from neat, composed pages to pages of scattered fragments, that gives your reading a direction. Time is the story you read off the album, not the paper itself. So why does time exist? Well, it's because the universe changes, because those changes leave readable records, and because statistical tendencies push reality from special low-entropy states to more generic, high-entropy states. From the timeless mathematical description emerges a practical, experienced time, the one your clocks measure and your memories rely on. If this video made sense to you, hit like and subscribe to Ionized Iguana for more videos where we pull apart the deep assumptions behind everyday reality. And tell me in the comments which impossible thought experiment you want to test next.